Okay. Good morning, everyone. I'm sorry that this took a while for us to start this morning, and the reason was had to do with connectivity, really. In spite of the fact that I have three different kind of data here, I still struggled a little bit this morning. So I'm sorry. Now, so we need to get to it quickly, so we don't waste more time. Okay. The last time we stopped at this example, so I told you that this morning we would be moving to rate law. Now remember that when we were defining chemical kinetics yesterday, we said chemical kinetics actually was about rate of reaction and mechanism of reaction. Now, there is a relationship between the two. In fact, you have an equation that actually speak to the relationship between the rate of reaction and the mechanism of reaction. And the link between the rate of reaction and mechanism is what we refer to as the order of reaction. Now, the rate law, because if kinetics is about rate of reaction and mechanism of reaction, what is the sequence? Now, the windows through which you do all this, or the windows through which you determine all of this, is the concentration of your reactant or your product. But more often than not, we tend to relate effectively, well, depending on the context, really, effectively weight the concentration of reactant. But of course, we can still use concentration of product. So now, the window is the concentration, the window through which you determine all this, either rate of reaction, rate constant, mechanism of reaction is the concentration. And what is the sequence if concentration is the window? You determine the rate of reaction from the concentration. Since we know that the rate of reaction itself is the change of concentration with time, or change in concentration with time. That's the rate of reaction. Now, after that, the next thing you want to do, you want to see what is the relationship between the change in concentration and change in rate of reaction. And that is the order of reaction. That is the order of reaction. The change, and I'm not saying that the relationship between concentration and rate of reaction. That's not what I'm saying. I'm saying that the relationship between change in concentration, not concentration now, change in concentration and change in rate of reaction, and not rate of reaction. So what I said was not the relationship between concentration and rate of reaction. No, it's the relationship between the change in concentration and change in rate of reaction. Now, it is now the order of reaction that they will now use to determine the mechanism or to speculate on the mechanism of reaction. I'll take that again for anybody who kind of like got lost or who missed what I said. Chemical kinetics is about the determination of the rate of reaction and mechanism of reaction. And in the middle there, you also have something called rate constant. But now, if that is what chemical kinetics is all about, and I said that the window through which you do all this, the window through which you determine the rate of reaction, the window through which you determine the mechanism of reaction is the concentration of your reactant or your product. Now, if the window is the concentration of your reactant, what is the sequence? Now, don't worry, we're still going to go through the slide. We're still going to explain gradually. I'm just giving a background to what our conversation is going to be about, because sometimes it is easier for students to follow when they know where you are going. Because what we want to do this morning is more about how do we use concentration and rate of reaction to determine the order of reaction. And what is the relationship between order of reaction and mechanism of reaction? That's what our conversation this morning is all about. And now we just want to give a background to what this conversation is all about. And that's why I said now, the window through which you do all this is your concentration. And how do you do this? What is the sequence? Since we know that we know that the rate of reaction is the change in concentration with time, then that means all you need to do when you add the concentration of your reactant is to look at how your concentration changes with time. That will give you the rate of reaction. So the first thing you want to do is you want to know the rate of reaction. When you know the rate of reaction, you can now move from the rate of reaction to order of reaction. You can just circle this sequence anyway. There is a way through which you can actually go through another route, but this is actually the elementary route. From your concentration to your rate, from your rate to your order of reaction. Now, your order of reaction is the relationship, because when you know your rate, how does your rate give you the order of reaction? The order of reaction is the relationship between change in concentration and change in rate of reaction. When you have your order of reaction, you can now use the order of reaction to speculate on the mechanism of reaction. I use the word speculate with all sense of responsibility, really, because mechanism of reaction, you start from speculations. You can now confirm whether what you speculated is correct or not. Now, but of course, it's not just a wide speculation. It's a speculation that must be consistent with the order of your reaction. Because what you have the order of reaction for is to be able to speculate on what the mechanism is, so you can now test which of your speculation is correct. Because you can have more than one speculation. You can have more than one possibilities. Which of them is correct? You can now do that by experiment. Now, let's now go through this gradually. You can now see what you have on the board is rate law. Now, rate law is actually the chemical equation or the mathematical expression that brings all this concept together. Your concentration, your rate constant, and the order of reaction. Rate law bring all this together. Now, at a fixed temperature, the rate of a given reaction depends on concentration of reactant. Now, the exact relation between concentration and rate is determined by measuring the reaction rate with different initial concentration. Now, you see that line is very important. And that's why when we see things in bullet point, we just think we need to read through. No, that line is very important because that line actually speaks to what I said. When I said you want to determine the relationship, between the change in concentration and change in the rate of reaction. And how do you do that? Of course, that means you want to measure your rate of reaction at different concentration. You want to measure the rate of reaction at different concentration. Now, then from that study, it is found, or from the study of your reaction rate at different concentration, of course, this directly now realize that the rate of reaction is directly proportional to the reactant concentrations, each concentration being raised to some power. Now, that power is what we know as the order of reaction. You know that all the parameters are present. And of course, when you remove your constant of proportionality, when you remove your proportionality sign and you want to introduce your constant of proportionality, that is your rate constant. Now, this is what I'm talking about. Now, your rate is found to be proportional to concentration, rate by some power. Now, that power is n here, and that is what we call the order of reaction. Now, when you remove your constant of proportionality, when you remove your proportionality sign, your constant of proportionality that comes into that equation is what is known as the rate constant. Now, when you have something like this, for a reaction with this molecularity 2A plus B to give you product, then the reaction rate with respect to A or B is now going to be determined. Now, when you have something like this, you can see we wrote the rate law. Rate is equal to K, which is the rate constant, A raised to power M, which, like I said, those power, they are your order of reaction. That then in this case, M A is raised to power m. Now that means m is the order with respect to A. We're coming to explain all this and how to determine all this. But we need to understand the original equation that we're going to be working with very well. Now, the B, which is the second reactant, raised to power n. Now, that means the n is the order of reaction with respect to B. Because at the end of the day, before the end of this part of CHM, this part of your chemistry course, this chemical kinetics, you will understand what the real meaning of the order of reaction. What does it mean when you're talking about mechanism of reaction? Now such expressions, or the expression you have there, this one or the original one, they tell the relation between the rate of reaction and the reactant concentration, because you have the rate, then you have the reactant concentrations. Like I said, that the rate law, this is what the rate law says. This is what we call the rate law. The expression which shows the reaction rate is related, how the reaction rate, is related to concentration is called the rate law. Now, the most important thing about that, those how are the order of reaction. The most important part, because if we just say, okay, that shows that the rate of reaction is related to concentration, then that means that, of course, we're going to be writing the same rate law for every reaction. But in this case, we say how it relates to concentration. How rate of reaction is related to concentration. Then that how is the order of reaction. That is what determines the relationship between the two. And that's what I said when I said that the relationship between the change in rate and the change in concentration is what we know, what is known as the order of reaction. Now, let's look at this. This is some chemical equations and the corresponding rate law. And we need to pay attention to some important fact here. Now, the first one, N2O5. Now, the rate is equal to N2O5. The rate is equal to rate constant multiplied by the concentration of N2O5. Now, you can see that you have two molecules N2O5, and the N2O5 is not raised to the power of 2 here. It's raised to the power of 1. Now, that is telling you that the order of reaction, or the power to which you raise your concentration in your rate law, is not the same thing as the number of molecules of that particular reactant, which is known as the molecularity. We'll talk about that also. So, meaning the rate of reaction, your order of reaction is not the same thing as the number of molecules. Now, for the second one, where you have hydrogen and iodine, your rate law is equal to rate constant multiplied by the concentration of hydrogen and concentration of iodine. Now, the fact that you have it as 1,1 in your equation and the other is also 1,1 in your rate law is just a coincidence. It does not mean that they are the same thing. It's just a coincidence. Same with the second equation. It's just a coincidence. And if you look at the fourth equation, you have one that has the same number of molecules, one that does not have the same number of molecules. That tells you that when they have the same number of molecules, it's just a coincidence. It's not the same thing because the concept remains the same. The concept through which you determine the order of reaction remains the same. There are times when it's the same as, and I'll explain what it means when it is the same. When you have the same number of molecules and your number of molecules is the same thing as your order of reaction, I'll tell you what it means. Now, in this rate law where the quotient of concentration is not shown, of course, it is understood to be 1. This is a university, not so we expect that you know that. Now, from those things we have shown, or from those examples, it is apparent that the rate law for a reaction must be determined by experiment. You can't just look at your chemical equation and write your rate law. No, you need to determine it by experiment. And we are coming to how to determine that. It cannot be written by merely looking at the equation with the background of our knowledge of law of mass action. No, the molecularity is not going to be the same thing. Now, for some elementary reactions, the powers in the rate law may correspond to coefficients in the chemical equation. That's what I was saying when I said sometimes when they are the same, you are probably dealing with an elementary reaction. That means you're talking about a one-step reaction. Because when we're talking about mechanism of reaction, more often than not, you're talking about, you want to write the stages in which that reaction took place. But when you find yourself where the number of molecules in your chemical equation, or what we call the molecularity, is the same thing as your order of reaction, then you are most likely, in most cases, you're dealing with a one-step reaction. And it will tell you the reason why that is so when we begin to talk about order of reaction. But usually, the power of concentrations in the rate law, are different from the coefficients. When I said that they're not the same thing, even when they look the same. The concept, or better put, we should say the concept is not the same. Because there are times when the order could be, well, equal, but the concept is not the same. They're not the standing two, but when you see them and they are the same, what it means is that you're dealing with an elementary reaction, and you'll understand that better when you know what order of reaction, what it really means, how does it determine, or how do you use it to determine the mechanism of reaction? Because we're still going to talk about that. That is the most important part of this course. Now, those for reaction 4 above, which one is, this is our reaction 4. You see the reaction 4 above. Then the rate is found to be proportional to hydrogen concentration, although the quotient of hydrogen in the equation is 2. For NO2, the rate is proportional to NO2, and the power corresponds to the coefficient. You see, that tells you that in this case, for that hydrogen, it's just a coincidence. Sorry, for the NO, it's just a coincidence. The concepts are different. But you will understand, you will know by the time you understand what order is, or how you use order to determine your mechanism, you will get a very clear picture of why you can actually have that for such coincidence for NO, for nitrogen oxide. Now, what is now this order of reaction itself? Because remember, we are saying that you can't determine mechanism without the order of reaction. You must know the order, because the order will tell you what the mechanism looks like. Now, what is the order of reaction itself? What does it really mean? I've told you what the mathematical meaning is, because when I said it's the relationship between the change in concentration and change in rate. That's a mathematical interpretation, really, because I'm telling you mathematically what does it mean, really? And you see why I actually said that. That's actually like a mathematical expression. But in terms of the chemistry itself, what does it really mean? Or at the molecular level, what are we talking about? Now, it is the number of atoms of molecule whose concentration change during the reaction, and these changes determine the rate of the reaction. Now, if you have a reaction where you have A and B, I'm just trying to explain what that expression means. Somebody is raising, and I just hope that it's a mistake, there's no problem. I do not want to take that for, okay. Aburi, is there a problem?
Sir, can you repeat that order of reaction again? The second definition. Not the one you said mathematically, the second one, the one you said normally.
Ask your question at the end of the class. Because if I begin to take questions in the middle of the class, then that means that, of course, if I'm not careful, I'm not even going to finish this. And I already made that clear the last time. We will leave 10 minutes at the end of the class to take questions, which I did the last time, and we're still going to do the same thing today. So this is a class where the time is short, and we want to make sure that we finish. For this content alone, you have 63 slides, and we're still on what now? 29 slides. We're not even halfway through, and we only have this class and next class to finish this, so we can go to chemical equilibrium. So you see, now I want to take this off. It's not going. Okay. Okay, now, because I can't come here and start reading slide, we need to make sure that we explain very well. I also come back to what I meant. You see, when I said mathematically, because that's what you will understand that when we get to how you determine the order of reaction, you will see why that was just a mathematical. What I said was an expression of mathematical relationship. So you will see it very clearly when we get to that point. So it's not something you need to worry about at this point. But now that first line, so when you have your A reacting with B, now if you have your A and B, say you have 0.2 molar of A and 0.2 molar of B, and you conduct your reaction and you measure the rate, and the rate is say 0.2 mole per dm cube per 0.2 mole per dm cube, sorry, per dm cube or per liter per second. And now you now change the concentration of, you now repeat the reaction. You change the concentration of A from 0.2 to 0.1, but you maintain the concentration of B at 0.2. You now measure the rate again. Now, if the rate remains the same, that is, you still have your 0.2 mole per dm cube per second, then that means that A does not affect, the change in concentration of A does not affect the rate of reaction. That means that A is of zero order in that reaction. Because you change, normally we say concentration, you remember what we said, that when the concentration changes, the rate changes. Now you're changing concentration of one reactant and does not affect the rate of reaction. Now what that means is that the order with respect to that, remember when we were writing this order of reaction, this is what, if you look at this now, if you come back to this equation based on that explanation, it means your M here is going to be zero. And that's what we mean when we say that it is the relationship between change in rate and change in concentration. Now, if you do the same for B and you get a, but if for A, when you change the concentration, you get a change in rate also, that means your M cannot be zero. But of course, we'll talk about how do you now determine what your M is. The same thing happens to N. But again, I know there's this question students always ask. When you say that about A, oh, we changed the concentration, but the rate did not change. They'll not be like, okay, that means we can even do the reaction without A. No, you can't do the reaction without A. Because what that is saying is that, remember, mechanism is about stages. Really, you want to write the steps in which your reaction took place. But what you're now, because what that means is that there is a stage that determines the rate of reaction. Because when you have a mechanism of reaction, remember, all those stages are not going to be at the same rate. Say you have step 1 of that reaction, step 2, step 3, step 4. They're going to be at different rates. Now, that step that is the slowest of all the steps, it is only that step, it is the rate of that step that will be the rate of your reaction. And that makes sense in the sense that if you have 4 people pulling each other, it doesn't matter how the fastest man of the 4 is, the slowest man will determine the rate at which you move. It's the same thing here, it's the same logic here. If you have a stage, you have a step in the reaction that is slow, it doesn't matter how fast all of that steps are, that slowest step will slow everything down because you need to wait for that slowest step. That is what will determine the overall rate of reaction. And now, what it means when you're now saying that A is zero order that when you change the concentration of A, the rate does not change, is that A is not present at that stage, at that slowest step. That A is not there at all. That is what it means when you, but of course, you still need the A at other levels, at other stages. But it's just not present at that point or at that rate determining step. And that's what we mean when we say that the slowest step in a reaction is the rate determining step. The slowest step is the rate determining step. No, so that is what it is saying, that the order of reaction is determined by the number of atoms of molecule whose concentration change during the reaction, and these changes determine the rate of the reaction. Order of reaction is also determined experimentally. We already mentioned that. If you cannot look at it from the equation, that means you have to perform some experiment. And even from what I just told you now, from the explanation you have now, you must determine rate before you know order of reaction. And you can only determine rate experimentally. It is also the sum of the powers of the concentration terms in the rate equation. Now, there is what we call the total order of reaction, or the overall order of reaction, and the order with respect to a particular reactant. Now, if you look at this equation, M is the order with respect to A, N is the order with respect to B, but the total order of reaction, the overall order for that reaction is going to be M plus N. So for this reaction, the order of reaction is M plus N. But the order with respect to A, the order with respect to B are M and N respectively. And that's what you have your rate is equal to. If you have more than 2 reactants, you can have your rate is equal to K N1, KC1 raised to power N1. That is the order with respect to N1. C2 raised to power N2, which is the order with respect to C2. Then C3 raised to power N3, which is the order with respect to N3. But of course, the overall order would be the addition of N1, N2, N3, and whatever those are. Okay. If I get, because I'm like I said, I've been struggling with, do I have to switch those 2 routers switched on here? But I hope I don't get kicked out, because if I get kicked out, somebody will have to come out for me to come. Okay, now, so this is the overall order. That means you add all the order together. And the order with respect to a particular reactant is the N1, N2, N3. Now, this is an example of the reaction order. For the first one, it is 1 because N25 is raised to power 1. For the second one, it is 2 because it is 1, 1 with respect to each of the reactants. For the third one, it is also 2 because NO2 is raised to power of 2. For the fourth one, it is H2NO2. It is 3 because H2 is raised to the power of 1. NO is raised to the power of 2 to make it 3. And I said that order of reaction can also be fractional. So in this case, it is 3 divided by 2 because this, which is 1.5, like we normally call it. So CHCl3 is raised to the power of 1 and Cl2 is raised to the power of half. Now, we cannot, so reactions generally are classified according to their order. Now, if in the rate law, your M plus N is equal to 1, you call that order first order reaction. Remember, the case where I said, okay, when you change the concentration of A, the rate does not change. Then that means the order with respect to M is going to be 0. That's an example. That means your M plus N is going to be 1. Or you can have A raised to power R, B raised to power R. So that makes it 1. Then if M plus N is equal to 2, you're talking about the second order reaction. If M plus N is equal to 3, you're talking about the third order reaction. Now, but there's also 0 order reaction. And I just explained that using A. Now, a reaction whose concentration does not affect the rate of reaction is not included in the rate law. That means you're going to take, because remember, concentration of A raised to power 0 is equal to what? Is equal to 1. That means you write your rate law without that reactant at all. Because what's the point? If it is 1, that means you should go completely missing in that reaction. And we already said that a 0 order reaction is one whose rate is independent of concentration. Now, at 200 degrees Celsius, the rate of this chemical reaction NO2 plus CO to give NO plus CO2 is written as rate is equal to KNO to raised to power 2. That means in this case, the rate does not depend on the concentration of carbon monoxide. So this is not included in the rate law, and the power of CO is understood to be 0. That's why it's missing. The reaction is also zero order reaction with respect to CO, and second order reaction with respect to NO2. So therefore, the overall reaction order is 2 plus 0 to make it 2. Now, what are we now? You see, what I explained generally the other time now, that's where we are. Now, if you have a reaction AB, if you have a reaction which is A plus 2B to give you D. Now, the last equation here in black, that is the overall reaction. But now, the mechanism of reaction is the first thing we have. It has been determined experimentally that the sequence of steps of a chemical reaction is as follows. A plus B to give C, that is the slower of the two steps, because this is a two-step reaction. Then the second step is C plus B to give you D. That is fast. Now, the question is now saying that what is the rate equation and the overall chemical equation? Because for a mechanism of reaction, what do you do to write? When you have a mechanism of reaction, what you do to write the overall equation is you add all the mechanism, all the steps, you add them together. If you add these two together, your C will cancel C, because you have C at the reactant side, you have C at the product side. You can't write an equation as you can't write the chemical equation and have something at the reactant side and something at the product side when it is not a catalyst. So that means C has to cancel C. Then the overall equation will be A plus 2B to give you D, because you have 2B at the reactant side, meaning that you have 2B, then 1A to give you D. Now forget about, you see, the reason why we wrote slow here, normally I'm not sure, but the reason why the slow is there is telling you that it is the rate of the slowest step that will be the rate of the overall reaction. Now, let's look at this logically. A plus B to give you C. It is slow. But C plus B to give you D is fast. Now, it doesn't matter how fast that second step is. It's going to have to wait for the product of the first step to do its own thing. Though it is fast, but hey, it doesn't have anything to work with at that rate. It will only work at the rate at which the first step is operating, because it needs the product of that first step to work. And that is why at the end of the day, the overall rate is going to be that of the first step. Even if the second step is the slow step, the first step can be fast. If the first step is fast, then that means it passes everything to the second step, which now goes at its own rate. So at the end of the day, you can't have your final product without that second step, and meaning that the overall rate will now be that of that second step. So the slowest step of any sequence of reaction is the rate determining step. Now, in this case, now you already have the mechanism, you add the two together. So the overall chemical equation will be obtained by adding the above equation to give you A plus 2B to give you D. Now, if you now want to write the rate law for this reaction, this is now telling you what order of reaction actually means. If you want to write the rate law for this reaction, now you are going to use the molecularity of the slow step to write your order, because essentially, order of reaction is just the molecularity of the slowest step. Order of reaction is the molecularity of the slowest step. And that is why when for an elementary reaction, the order of reaction will be, the elementary reaction is a one-step reaction. It doesn't have any mechanism, it's just a one-step reaction. And that is why for an elementary reaction, order of reaction will be the same thing as the molecularity of the reaction. Because at the end of it, it's just one step. And that one step is, you can't have any faster step, you can't have any slower step. It's just the one step. So you want to write the rate law, you are going to have to include all the elements. So, and that is why in this situation now, what you see here, which is A plus B, that is your slow step. And that is what you're going to use to write your rate law. Now you have your rate is equal to K, concentration of A, raised to power, what is the molecularity of A, or what is the number of molecule of A in the slow step? It is 1, A raised to power 1. B raised to power, what is the number of molecule of B in that slow step? 1 raised to power 1. And your rate is equal to K multiplied by concentration of A raised to power 1 multiplied by concentration of B raised to power 1. Now, we've been talking about rate. We've been talking about rate and rate constant. Rate constant. Rate constant. Now, what are the differences between the two? Because remember, we said if you look at that equation, there's a rate. There's a rate constant because that is what it is the rate law that brings all these elements together. Now, what is the difference? Now, for all orders except zero order, and we already said that for zero order, it doesn't matter what you do with concentration, rate will remain the same. But except for zero, so zero order reaction, rate remains the same. Except for all orders except zero order, the rate of reaction varies with concentration. And it's a useless means of quantifying reaction or comparing reaction. If you want to compare two reactions or you want to compare the rate of two reactions, you can't use rate of reaction. Even for that single reaction, the rate of reaction is not even constant. It drops as the reaction progresses because the concentration changes. So rate of reaction is useless as a means of comparing or quantifying reactions because it doesn't stay constant. In contrast, the rate constant is a constant at a given temperature and is independent of concentration. So a rate constant, it doesn't matter what you do to your concentration, that thing you call rate constant must be true to its name as long as the temperature remains constant. And it is only rate constant that you can actually use to compare reactions. So if you know your rate constant and the order, if you know rate constant and you know the order, you can calculate the rate of reaction for any concentration. Because remember, we have this expression between all of them. The rate is equal to Ka. I'm talking about this expression. If you know your rate, if you know your concentration, you know your rate constant, and you know the order of reaction, you can calculate the rate for any combination of concentrations here. Because you know your rate, you know the order, and you know the concentration. You know your rate constant, you know the order. You just need to look at what concentrations are you working at. That will give you what your rate will be. Because rate will be the only unknown. Now, molecularity of a reaction. We're still coming where we just need to quickly branch and do something related before we come to those order of reactions again. Now, chemical reaction may be classified into two types. We have elementary reactions, I already said that, and complex reactions. Elementary reaction is a one-step reaction. A complex reaction is a reaction that proceeds in two or more steps. And that is why for elementary reaction, I already told you, you are going to be having the same, your molecularity will be the same thing as your rate. As the order of reaction. While for complex reactions, you can hardly get something like that. Now, the molecularity of an elementary reaction is defined as the number of reactant molecules involved in that reaction. Thus, the molecularity of an elementary reaction is 1, 2, 3, etc., according to the number of participant reactants. Now, if you have a reaction, hold on, okay, I wanted to be sure that we have those examples. So the elementary reactions having molecularity of 1, 2, and 3 are called unimolecular, bimolecular, and thermomolecular respectively. That is, if you look at this, a unimolecular reaction, you only have just one molecule to give you the product. And that is, the molecularity is 1. You have one molecule in that reaction, as a reactant in that reaction. Molecularity is 1. That's a unimolecular reaction. The second example, which is for bimolecular reaction, that means you have 2 molecules of reactant. That can be in 2 forms. You can have A plus B, which still make it 2 molecules. You can have 2A to give you product. Molecularity is 2, and that's a bimolecular reaction. And you have examples also there. Then you have thermolecular reaction, meaning that the molecularity is 3. You have A plus B plus C. You can have 2A also plus B. The most important thing is that the number of molecules must be 3. It can even be 3A. It doesn't have to be A plus B plus C. It can even be 3A. It can be 2A plus B. It can be 2B plus C. The most important thing is that the number of molecules must be 3. And that will be a thermolecular reaction. Now, we've spoken about this extensively, the difference between molecularity and order of reaction. And we already said that they are not the same. For the concepts are completely different. And that is why when you get the same thing for an elementary reaction, I said order of reaction is going to be the same thing as molecularity. That doesn't mean the concepts are the same. It's just that for an elementary reaction, you only have 1 step, and that 1 step is the slowest. You can't say slowest step. It's the only step. And the rate of that step will be the rate of the reaction. The total number of molecules or atoms which take part as represented by chemical equation is known as the molecularity of the reaction. We already explained that. Why the sum of the powers to which concentrations are raised in the rate law. These are just repetitions of the definition of each of those concepts. Now, the rate of an elementary reaction is proportional, because when we started this, one of those things I said was that you remember when I was talking about our order. Okay, I think we're going to have to stop here so that I can take your questions. Because somebody I like to leave 10 minutes, and now this is 9:52. So please, your question. So I think we should be able to finish the remaining 20. Because for this topic, we have 63 slides. I think we're already on 40 something slides now. I want to be sure. Where are we? Okay, we're still on molecularity of reaction. So, okay, I think we're on the 40. Okay, 40 slides. So we should be able to finish the remaining slides next week. So the following week we'll go to chemical equilibrium. Now, your question. Raise up your hand if you have a question. Aburime Eromosele. Unmute. Hold on before you ask your question, because I like to take it together. So can I write a question down? Okay, I'm listening.
Okay, sir, please. You said you gave 2 definitions of order of reaction. Please, sir, can you say it again, sir, please?
I didn't give 2 definitions. I said
you gave one mathematically. Sir, you gave one mathematically. Then you gave one like normally, the normal definition.
I said, okay. You see, the mathematical one, I said that it is the relationship between the change in concentration and change in rate of reaction. It is the relationship between the change in concentration of a reactant and change in rate of reaction. Why the second one is what you're actually having on your screen now. The sum of the power to which the concentrations are raised in the rate law.
Oh, okay. I wrote that. Thank you, sir.
So then that first one, you'll understand the concept when we actually explain how to actually determine the order of reaction. We've told you what the concept is, but at the end of the day, what is that number? Is it 1? Is it 2? Is it 3? How do you determine that? You'll understand that concept better.
Yes, sir.
Okay, now, okay, that's your question. Lamino Yamal, your question. Okay, so you can unmute now. Okay, he's gone. I can't see him again. Maybe it's network. Okay. Anya Ogochukwu, unmute, please.
Hello, sir.
Yeah. Go on. Ah, God. Okay, did I am going to go on mute because I thought I unmuted you.
Okay.
Okay, go on. What's going on? I think are you the one fiddling with your phone or something is going on here? On mute. Okay,
I'm
the second
unmuted.
Okay, if that happens again, I'm going to the next person.
Hello.
Your question, please. Delight, your question, please.
Sir, can you explain come again with the how to get the molarity, like the what's the name? The molecularity, that's like
Molecularity of a reaction.
yes.
Okay. All right. Then mute yourself again. Abe Temi Dayo. Unmute, please, and ask your question.
Good morning, sir.
Good morning.
You mentioned that molecularity is different from the order of reaction.
Yeah.
Please can you explain how we
Okay. Order and
can
molecularity.
actually find the order of reaction? Because I didn't really.
How you okay? That question again. You lost me. You're breaking up already.
We could show the molecularity already, but how do we find the order of reaction?
I already said that we are still going. We've not spoken about how do you determine order of reaction. It's going to be one of those things we're going to talk about on Friday. We have not discussed how to find. We have not discussed how to find order of reaction, but we're still going to talk about it because we only talk about the concept and what it means.
Okay.
How do you actually determine? Yes, we'll talk about it in our next class. Then Oluwa Darasimi, unmute and ask your question, please.
Good morning, sir. So I wanted to ask that how do I determine the stages of reaction or the power of the concentration in rate law? Because they said they are not equivalent to the coefficient.
Okay. 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 I'm going to take that again because sometimes when students ask questions, even if it's something you said over and over again, now maybe it's kind of like drive his own better. Now, there's something I said that number one, we've not discussed how you determine order of reaction. We've discussed what it means. So you wait for next class before you get how do we actually determine that number? Is it first? Is it second? Is it third? Now, but you're saying that okay, that they are not the same. We said it so many times that you determine order experimentally because if order is dependent on rate and you can only determine rate experimentally, it's only logical that of course order of reaction can only be determined experimentally. I will talk about how you do that next class. But with molecularity, of course, you just look in your equation and whatever the number of molecules in the overall equation is, that's the molecularity of the reaction. Count the number of molecules. When you count the number of molecules, then that tells you, I'm trying to go back to that example that we did. Okay, look at this example. A plus B, that's bimolecular because we have two molecules. A plus A, bimolecular, two molecules. A plus B plus C, thermolecular, three molecules. And under the example, you can see we have 2NO plus O2. That means that, of course, that general example can actually be 2A plus B or A plus 2B or A plus 2C, as long as you have three molecules. It can even be 3A. But order of reaction is determined experimentally, and we'll talk about how to determine that next class. Okay, I hope I answer your question because okay, that was from Oluwadara Senior. Then Bolaji, did I answer your question? Bolaji, Omo Pariola, unmute please and ask your question.
Good morning, sir.
Morning.
Sir, please, can you please re-clarify on the zero order reaction?
Okay, now zero order reaction, what we remember that the general concept is that when the concentration changes, the rate of reaction changes. But when you now have, say you have reactant A and B, But okay, I think we have a very good example that we show there. I think I better go to that example where I found that example. Okay, now look at this. NO2 plus CO to give you NO plus CO. But now let's now look at this example. Say you have this example. You have 0.1 molar of 0.2 molar of NO2 and 0.2 molar of CO. You measure the rate, and the rate is 0.2 mol. Well, say the rate is 0.1 mol per dm³ per second. Now you now repeat that same reaction. You now change the concentration of CO from 0.2 to 0.1, while you retain that of NO2 at 0.2. You now realize that you still have the same rate of reaction. The rate of reaction still did not change. That means that when you change the concentration of that CO, it has no effect on rate. What that means is that the order with respect to CO, it is zero. It is zero. A zero order reaction is one, or a zero order reactant is one whose rate is independent of concentration. In this case, it's just a reactant. And you can actually have a reaction where they are just zero order. You change the concentration, nothing changed to the rate. Nothing changed, the rate still remains the same. So that means the whole reaction is a zero order reaction. While in this case, it's just one reactant that is actually giving that kind of performance. That means the order with respect to that one reactant is zero. So any reaction where a concentration change does not lead to a rate change as expected from the general concept of change in concentration must lead to change in rate, that reaction is a zero order reaction. If it is not your reaction, if it is just a reactant, that reactant is zero order as far as that reaction is concerned. Temitope, please, Akinwole, your question, please. Okay, unmute.
So please, can you go to rate law, the slide on rate law?
That's our first slide.
Yes, no. You passed it already. So keep going. No, this one, yes. Okay, is it this one? No, it's not this one. There was one where you wrote, yes, there was one where you wrote the molarity, like in front of the equation.
I wrote the molarity.
Yes.
This
yes,
one.
this one. This one.
This one. Which one?
No, it's not this one. It's not this one either. Yes, this one.
You already said it's not this one. Okay. How about this one?
No, you wrote the molarity for each product in front of the reaction. So I don't understand how you got that. Yes.
No, well, I don't know. I'm not sure I know what you're talking about. Okay. Well, let's go up a little bit. Well, no, I don't know what you're talking about. No, so I don't even know the slide. So these are all the slides we ran through today. So if you still can't find it, then maybe you saw that slide in your maybe you saw it in your imagination. So because I already ran through all the slides. Okay.
Okay.
Unmute please and ask your question. I don't have that time to start running through slides again. Already.
Hello, sir.
Hello, yeah.
So you said we can find the power of the concentrations in the rate of reaction through the coefficient of the slowest reaction.
Okay, go on.
Can we use that method to find the order of reactions too?
You see, everything you spoke about, you see, I didn't tell you that because I'm not sure how you even said it now. Because what I said was that, you see, that coefficient you're talking about is the order of reaction. Sorry, that power that you're talking about, the power to which you rate your concentration in the rate law is the order of reaction. That is your order of reaction.
Okay, so
I'm trying to get.
And it can be found through the coefficient of the slowest reaction.
Hold on. Yes, it's the same thing. Thank you very much for the way. It's the same thing as the coefficient of the slowest step in your mechanism of reaction.
Okay, sir.
All right. Okay, next let's see. Precious, are they unmute? Are they your unmute, please?
Okay, sir, when you gave us rate law and reaction order,
Mm-hmm.
on that slide, I didn't quite get how you got the reaction order. Oh,
I already said that. Okay, are you talking about this?
yes, sir, this slide.
Okay, now if you look at it, we're just adding the power to which we rate it. If you look at it, this is raised to the power of 1. This is 1. So the reaction order is 1 because at the end of the order of reaction is the power to which you raise your concentration in your rate law. In the second one, H2 is raised to the power of 1, I2 is raised to the power of 1, 1 plus 1 is equal to 2. That's your reaction order. NO2 is raised to the power of 2. Your reaction order is 2. The fourth one, H2 is raised to the power of 1, NO2 is raised to the power of 2. Your order is equal to 3, 1 plus 2, and so on. So that's it.
Oh, okay, sir.
Okay, Agbaje Bali, okay. Agbaje Bali, please, Omotolani, ask your question, please. Or mute and ask.
No, sir. So I want to ask if you can go back to slide 20, sir. I'm slide 30, sorry, sir. Slide 30. Thank you, sir.
Okay. Yeah, we have it. That's it. That's like 30, Abby. Are you still there? You're muted already. On mute, please. You're muted. I thought you were asking a question. So, okay.
No, it's all right, sir. Thank you, sir.
Okay, Basti Sumola. Well, I'm still going to give you the slides anyway. So,
good morning, sir.
Basti Sumola. Yes.
Good morning. So
and that'll be the last question for today.
So the guy before me said that to determine the order of reaction, it can be determined by the rate of the concentration of the slower reaction. Am I right?
It is the order of reaction. It's the power, sorry, it is the coefficient of the slowest step, or is the molecularity of the slowest step.
Okay. So what I want to get to is, you said that in the normal sense, the order of reaction can only be determined experimentally. So we can only know the reaction that is actually slower if you actually perform the experiment.
Definitely. You won't know, well, you won't even know the stages if you don't perform experiment anyway.
Thank you.
All right. Okay, so good morning. So I'll see you on Friday. And please take note of where we stopped. I think we stopped at slide 30, slide 40. So because I struggle with that. So if you don't remember where we stopped, you might just find me going to slide 50. And that'll be on you. So good morning.